Hello, students. In this lesson, we will be starting Unit 2, talking about probabilities. And this unit is going to start in Chapter 5. So let me pull up my screen. There we go. So today we will be talking about Chapter 5.1, our probability rules. So we're going to get us going in probabilities. Now there are going to be some definition and terms we need to know. Our sample space is the set of all possible outcomes of an experiment. The event is just some subset of that sample space. A simple event is a single outcome that cannot be broken down any further into simpler components. So each element in a sample space is considered a simple event. So for an example of an event that is not simple or cannot be broken down any further would be the event of rolling 2 dice and getting a sum of 10. Well, as you will notice, if we take 2 dice and roll it to get a sum of 10, we have more than one way to get that sum. We could roll a 6 and a 4 or a 5 and a 5. So this would not be considered a simple event. Then we also have the probability. The probability of an event is the likelihood that the event will happen as a proportion out of 1 or a percentage out of 100. So you guys, a probability is always, always, always a proportion. Next, we're going to talk about how we find those sample spaces. Well, once again, a sample space is just all of our possible outcomes. So if we want to find the sample space of a single 6-sided die that is rolled, well, in that case, our sample space is going to be all the possible outcomes on that die. Well, that's just the numbers 1, 2, 3, 4, 5, and 6. Those are the numbers you will find located on a normal 6-sided die. So that would be our sample space. We can do the same thing if we flip 2 coins. So what we do is on our first coin flip, pull this guy in here, on our first coin flip, we could get either a heads or a tails. On our second coin flip, same idea, we could either get a heads or a tails. The issue here is, what did we get first? So what we really have are 4 different possible outcomes for our sample space. Our first guy for our outcome, well, we could have a heads and then a heads. We could also then have a heads and then a tails. We could have a tails and then a head. Or our last outcome would be a tails and then a tails. So this should be green. There we go. So we have a total of 4 different possibilities when we flip 2 coins. We could first get a heads and then a heads and then a tails and then a heads, or a tails and a tails. Now, if you notice, order matters. Because we are talking about flipping 2 different coins, so these 2 events here are, because the order does indeed matter. So let's look at one that's a little bit more difficult. If we want to find a pair of 6-sided die and record all those possible outcomes. Well, I know when I have a six-sided die that my first die, I have the numbers. So my first die, I'm going to make it red or purple. I have the numbers 1, 2, 3, 4, 5, and 6 for my possibilities of that die. So that's my first die roll. I know my second dice, I could also get 1, 2, 3, 4, 5, or 6. So then together I get multiple different outcomes. I can get the outcome 1, 1. I could get the outcome 1, 2. Once again, it all depends on the way or the order that they come up. Order does matter. So as you see, I'm just going to continue filling out this chart. Now mine ends up being pretty messy. So what I did is I'm going to erase everything we have here, and I'm going to pull in some pictures to make it look a little bit prettier. But that was the idea of how we're going to then get these two charts. So this is what I was doing right here. I was making a chart. Our first guy was 1, 1. These would be our two separate dice rolls. If that's kind of hard to see, here is an actual picture of if we were to roll our two separate dice. So we end up, if you were to count all of the possible outcomes in this guy here, we would end up with a total of 36 different outcomes you can get when you roll two six-sided dice. There will be 36 outcomes you can possibly get, or your sample space will be these 36 events on the inside. For just to make sure you understand what's going on, this guy right here would be the event if I first rolled a 4 and then I rolled a 3. So these are just all the possible events for rolling my die. All right, so as we continue on, what you're going to see is some new notations. A capitalized S, which you saw me use up here. A capital S is going to represent the sample space, all those possible outcomes. Then we can use any other capital letter. It really doesn't matter which one. They're just like variables. And those variables are going to represent other outcomes. And we'll get into that a little bit later. Then just like the previous units, what we'll see is X is used to represent several events. Then another something we're going to need to know is that if we have N and then some capital letter, it is used to represent the number of elements that are made up in the event or the sample space. So really depending on what we named our event, if we named our event, let's say B, and we had the elements 1, 2, 3, and 4 in B, we could say the number in event B is 4. There are 4 numbers there. So this letter can really be anything. The N just stands for the number in that of events in that sample. All right. So next we're going to talk about how to find those probabilities. If a sample space consists of only simple events that are all equally likely to occur, they're all equally likely to occur, then the probability of event, we can set up event A. We can call it the number in that event A divided by the total number in our sample space. Because the sample space size is always greater than or equal to the size of the event, because that sample space is everything in that event, the probability is always going to be between 0 and 1 inclusively. That means that it can be 0 and it can be 1. So if we ever get a probability of 0, that means that the event is impossible. It is never going to happen. If we get a probability of 0, that event is impossible. It is never, ever, ever going to happen. Then if we get the probability of 1, that means that we are certain the event is going to occur. It is going to happen, and we can guarantee it if we get a probability of 1. So let's look at some examples. If a single dice is rolled, we want to know the probability of rolling an even number. Well, let's first talk about the sample space for a single die rolled. I know the sample space is going to be the numbers 1, 2, 3, 4, 5, and 6. Those are all the possible numbers I could roll on a dice. Then what happens is they want us to roll an even number. I'm going to name this outcome of an even number just because I can. We'll name it A. So the event space A are all my possible even numbers out of my sample space. So that would be 2, 4, and 6. Those are all my possible even numbers out of a single-sided dice. Well, now that I found these two actual events, what I can say is I know from our previous slide that the probability of A is equal to the number of things in A divided by the number in our sample space. Well, if you notice, the number in A is 3. We have 3 different numbers in there. For S, we have a total number of 6. So when we go to calculate our probability, we're just going to say 3 divided by 6, or 0.5, or we have a 50% chance to roll an even number. Next, we want to know the probability of rolling an 8. Well, I'm going to name that probability just so it's easy to talk with. The probability of rolling an 8, I'm going to name B. So once again, I know the sample space for the dice. Our sample space is 1, 2, 3, 4, 5, and 6. Then when I look for the probability, or I'm looking for rolling an 8. Well, if you look up here, there's no opportunity to roll an 8. So there's nothing in B. Well, that means the number of events in B is 0. We still have the number of events in our sample space is 6. But what we once again know is we know we're looking for our probability, or we have 0 divided by 6, which in this case is 0. Well, we know that we are never, ever, ever, ever going to get an 8 when we roll a 6-sided die. So basically, it is impossible to roll an 8 on a 6-sided die. It is impossible. Well, because it is impossible, what we end up with is a probability of 0. On the other hand, what if we want to roll a number less than 8? Well, I'm going to call rolling a number less than 8. I'm going to call that event C. Once again, we have the same sample space. 1, 2, 3, 4, 5, and 6. I'm then going to call find everything My event C is going to be every single one of these numbers that is less than 8. Well, all of these numbers, 1 through 6, are indeed less than 8. So they all follow the rules and can go into our event C. Well, if you notice, the number of things I have in my event C are 6. I also have 6 in my sample space. So when I divide those out, when I say 6 divided by 6 to find my probability of event C, I end up with 1, or I am certain every single time that I roll that 6-sided die, I will for sure come up with a number less than 8. So 100% of the time, I will be rolling a number less than 8. So this next one, if 2 coins are flipped, what is the probability that at least one of the coins lands on head? So I'm going to call this next event. I'm just going to keep on going down the alphabet. At least one coin landing on heads. That's going to be my event D. And then I have to remember that my sample space for flipping 2 coins, well, that's going to be heads, 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 tails, tails, heads, and tails, tails. Well, then if I want at least one heads, that D looks funny, there we go. Well, here's at least one. This one has at least one heads, and so does this guy. So it looks like I have 3 numbers, oops. I have 3 numbers in my sample space that fill out that rule or are less, have at least one heads. So the number in D is 3. The number in our sample space is 4. So the probability of D would be 3 out of 4, or 0.75, or 75% of the time we will, so 75% of the time, at least one of the coins will land on heads. Next, we're going to talk about that pair of 6-sided die. So before we go too far, what I'm going to do is I'm going to put all of those pairs in, because once again, we do need to know what our sample space is. I don't like that that 6 came up. Let's see. There we go. So what I'm going to do is I'm going to recopy that sample space in. So there we go. There's my whole sample space. Y'all, having this sample space near you during your homework will be handy. The homework questions love using this guy. So our sample space are these 36 outcomes. This is going to be our sample space for 2 or a pair of 6-sided dies. Now we want to find the probability of getting a sum of 7. So let's, in this sample space, find all of these sums of 7. Well, 4 plus 3 is 7. 5 and 2 is 7. 6 and 1 is 7. Once again, order matters. 3 and 4 is 7. 5 and 2, or 2 and 5, and 1 and 6. So if you see all those there are our ways to roll and add to 7. I have a total of, for let's say a sum of rolling a 7, we'll call A, B, C, D, E, we'll call this F. Let's do to where it writes. There we go. We'll call this guy F. And it looks like to find F, there are 1, 2, 3, 4, 5, 6 different outcomes. I know our sample space has 36. So the probability of F will be 6 divided by 36. Or when we put that in our calculator, that would be 1 out of 6, or 0.166 repeating. Or when I round, I can just say that that's about 16.7% of the time we have the probability of getting a sum of 7. Next, it wants a sum greater than 8. They want a sum greater than 8. So I'm going to look back up at our possibilities. So we're going to look at all of our possibilities, and we want strictly greater than 8. So 9, 10, 11, or 12. Well, here are all of my 9s. We have my 10s. We have here is adds to 11, and here I add up to 12. So now I want to know the total number there. Well, I ended up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number where we have a sum greater than 8. Well, we have 10 of those. We once again know that we have a total of 36 in our sample space. So the probability of a sum greater than 8 would be 10 out of 36, or 0.277 repeating, which will give us a probability of 27.8%. So 27.8% of the time, we will roll a sum greater than 8. Next, we're going to talk about the empirical probability. The empirical probability, basically some events and sample spaces cannot be broken down into simple sets like bags of marbles or decks of cards. For some events, we will calculate the probability by using statistical evidence. We are going to calculate the probability by using statistical evidence. When we have to calculate the probability, not with decks of cards or marbles or sample sets, when we have to use statistical evidence, it is called the empirical probability. When we do that, the formula isn't too much different. It's still going to be the number of times that event has occurred divided by the total number of trials in the experiment. We also have a rule called the rule of large numbers. And you guys, you are going to see this rule over and over again as this class continues forward. The law of large numbers states that as the number of reputations of a probability experiment increases, the empirical method becomes more accurate. So basically, the more reputations, the more we do the experiment. As we increase the number of reputations, I'm bad at saying that word, we become more accurate. Then what we're going to do is we're going to find another way to find unlikely events or unusual. If we find the probability is less than or equal to 0.05, we are going to be considered unusual. So let's take a look at an example. So over the past 10 years, a person has gone on 530 hikes and sprained their ankle 4 times. So we want to consider if this would be considered usual or unusual. Well, once again, you guys, we know that the formula is the number of times A has happened. Well, in this case, we're talking about the number of times we have sprained their ankle. Well, we've sprained our ankle 4 times out of a total of 530 hikes. So the probability of spraining my ankle, the probability of a sprained ankle will be those 4 times it actually occurred out of the total of 530 hikes. When we put that guy into our calculator, we end up with 0.007547. Well, they want to know we're not quite done. So this is the probability that we're going to sprain our ankle on a hike. But they want to know if it's considered usual or not, or unusual. Well, so what we're going to do is we're going to compare this number to 0.05. Well, because 0.007 is less than 0.05, we know that this guy right here, we do indeed know that it would be unusual, unusual, to sprain the ankle. It would be an unusual occurrence to sprain my ankle on a hike. Our last slide for this section, we're going to talk about probability models. A probability model lists all the possible outcomes along with their probabilities. The sum of these probabilities must always add to 1. The sum of the probabilities must add to 1, and then each individual probability must be between 0 and 1. You guys, they're going to look a lot like our percent, why can't I think of the word? Our frequency table, our percent frequency tables. They're going to be a lot like the same thing. But the first rule is that every number does indeed have to be between 0 and 1. Well, that's the first thing I'm going to check in this first chart. Well, if you notice, each one of these probabilities is between 0 and 1. So our first rule, or our second rule in this first part, checks. I'm then going to add everything together. I'm going to find the sum of these guys. Well, when I add them all together, I get 0.78. Well, because 0.78 does not equal 1, this guy here is not, we are not a proper model. This first one is not a proper model. So let's check the second one. Well, first, all the numbers are indeed between 0 and 1. So our second rule checks. Now let's check to see if we sum to 1, because that is the second rule. And when we add all these together, we do indeed get 1. Well, because we add to 1, this guy checks as well, and we know this guy is a proper model. That's all you have to do to check if your probability model is correct. All of our probabilities have to be between 0 and 1, and then everything has to add to 1. That is all I have for section 5.1. If you have any questions, please make sure to email me.